As we've seen in previous topics, halogenated alkanes have a whole range of reactions that is available to them. And those are SN2, SN1, E2, and E1 reactions. And so at times it becomes quite difficult to see what will happen under a certain set of conditions, which one of these four reactions will predominate, and whether there will be a single one reaction predominant. Now, analysis of this distribution of products is pretty complex, and it depends. It should really be done on a case-by-case basis by carefully looking at the reaction conditions. But this subtopic will give you a set of general guidelines that you can use in making that decision. It's important to realize that this is not a flowchart, that you cannot just say, well, this is a set of rules, and you simply get your reaction that's going to happen by applying a set of rules. You have to look at these things case by case, but once you do that, the relatively consistent picture will emerge. In order to do that, the first approach that we're going to take is look at the nucleophile. And so, depending on which nucleophile we use in our reaction can take different courses. So, if we have a good nucleophile, which is also a weak base, and examples of these are iodide, azide, phosphines, cyanide, carboxylates, etc. These nucleophiles are good nucleophiles. They will favor substitution reactions, especially since they're also weak bases. And so they will go into SN1 reactions with tertiary substrates, but into SN2 reactions with primary and secondary substrates. With secondary substrates, since they're good nucleophiles, they will not have to wait for the cation to be formed. They'll just jump right in and get the nucleophilic reaction going. But now if we have a weak nucleophile, which is also a weak base, and we've seen examples of these in water or alcohols, etc., then we will still get SN1 reaction with secondary and tertiary substrates. Again, because in these cases we can form a cation, and once we do that, then the nucleophile doesn't really matter. And we will get some minor E2 reaction as well. Minor E1 reaction as well. So if we start with this 3-bromopentane and treat this with water, our major product will be 3-pentanol. This is about 85% yield. But we will also get some of the pentene, about 15%. Importantly, since these nucleophiles are weak base but also weak nucleophiles, they will not react in SN2 reactions, and so the primary substrates will really not react with these species at all. Okay. What about the nucleophiles that are good nucleophiles but also good bases? Let's look at them a little. Look at them on the next slide. In these cases, we will get a mixture of the substitution. I'm sorry, this is ethoxide. We'll get a mixture of substitution and elimination. So in cases of primary substrates, we'll get mostly substitution through SN2 mechanism. But we will also get, in case of, get some elimination. Now, if we have a primary substrates which are branched, we will still get some substitution, but now it will be a minor product, while our major product will be E2 reaction, 60% yield. If we go for a completely secondary substrate, such as this 2-bromopropane, then we will get very little, just 13% of this, and 87% of our elimination product. So this is mostly E2 now. And finally, in the case of tertiary substrates, the steric bulk is so large that we will get exclusively E2 product in that case. So what we see in these cases is that basic nucleophiles what we see is that increased steric bulk in substrate matters. The reason for this is simply that E2 reaction is sterically less demanding than SN2 reaction because it occurs on a proton while the SN2 reaction occurs on a carbon. And this is highlighted by our next example when we have sterically bulky and also basic nucleophiles, which give us exclusively, well, not exclusively, but dominantly E2. Here's an example. We start with 1-bromobutane and treat this with potassium T-butoxide, so a sterically bulky version of this etoxide, to get 85% of elimination product, but also just 15% of our substitution product. Examples of these bulky bases would be things like T-butoxide, or lithium diisopropylamide. Also known as LDA. And these are used to get almost exclusive elimination. In summary, we need to look at three main factors when analyzing this. So the first one is basicity of nucleophile. And in cases when we have weak bases, these will favor substitution. If nucleophile is strong bases, we will favor elimination. Examples of weak nucleophile bases are things like water, alcohol, PR3, halides, sulfonates, azides, cyanides, etc. The strong nucleophilic bases are things like methoxide, hydroxide, amides, and so forth. And since they're strong bases, they will increase the likelihood of elimination. The second factor we need to look at is steric hindrance in substrate. And this is steric hindrance on the reacting atom, reacting carbon of the substrate. If we have a sterically unhindered primary thing, then we will favor substitution. If we have a sterically hindered secondary or tertiary or even branched primary, we will favor elimination. And again, this is, comes from the fact that elimination is sterically less demanding reaction, so it operates well on sterically bulky substrates. Finally, and this is where the last point comes in, is that the steric bulk of nucleophile matters as well. And so if we have nucleophilic atoms which are sterically hindered, such as T-butoxide or lithium LDA, we will strongly favor elimination. But if we have basic nucleophiles which are not so sterically hindered, such as methoxide or hydroxide, we can still get significant substitution. Finally, one additional way we can look at that is through analysis of a substrate. And so we can see, and of course these two analyses are complementary. But if we look at the primary haloalkanes, and if we expose them to strong nucleophiles, we will get SN2 reaction. This is pretty typical. If we expose them to hindered bases, we will get E2 reaction. And finally, if we expose them to weak nucleophiles, we will get no reaction. In other words, whatever we do, we cannot get primary haloalkanes to undergo either E1 or SN1 reaction. Secondary haloalkanes are the most difficult to analyze because on one hand their steric bulk is not too bad, so sometimes it can allow the SN2 or E2 reaction. On the other hand, they do form stable cations, they go into SN1 and E1 as well, and so they're sort of a borderline case. So in cases when we have extremes, such as a good nucleophile, we will get SN2 reaction in this case as well. If we have a strong base, we will get E2 reaction, just like in the case of primary. But if we have a weak nucleophile or a weak base, then we will get a mixture of SN1 and E1 reactions. And oftentimes these mixtures are exactly what we get in the SN2 reaction of secondary haloalkanes. Finally, the tertiary haloalkanes with strong base, they will give E2 reaction. So remember, E2 reaction can occur in tertiary substrates as well. If we have a base that is strong enough, that doesn't need to wait for the cation to kick. If we have no base, or if we have weak base, then we will get a mixture of SN1 and E1. And these mixtures are very difficult to avoid, because once we get a tertiary cation or so, it's difficult to guide that cation, which is now the same for both E1 and S1 reaction, towards one or the other. Okay? And then finally, one thing that will never happen is SN2 reaction on a tertiary haloalkane. So there are certain possibilities you certainly can exclude. In primary haloalkanes, this is SN1 and E1 reaction. In tertiary haloalkanes, is the SN2 reaction. But everything else, most of the other substrates, is on the table, and so that it needs to be considered. And finally, before we finish, we also need to remember a couple of other points, and that is solvent. So for SN1 and E1 reactions, we want polar product solvent that will stabilize the cations. For SN2 and E2 reactions, we would prefer polar aproduct solvent. A couple of other points is that E1 and SN1 reactions occurred with rearrangements. That E2 and SN2 reactions have no rearrangements. E1 and SN1 reaction racemize whatever chiral starting materials you might have had. E2 and SN2 reactions are stereospecific. And finally, the eliminations E1 and E2 follow the Zaitsev's rule, which means that in cases where multiple possible alkenes can be formed, the most stable, which is the most substituted alkene, is formed predominantly. So together with our previous two lectures, this lecture concludes our treatment of reactions of haloalkanes. And I hope that a relatively complex but consistent picture emerged. There are 4 possible reactions, and that you can guide to a certain extent these reactions towards one or the other direction by the appropriate choice of reaction conditions. But this is not absolute, and there are no flowcharts which allow you to predict what exactly will happen, and you have to look carefully at all the substrates and understand their roles and their activities in every specific case. That's it for today. Next time we'll start talking about the products of elimination reactions, and those are the alkenes.